Okay, waves 1. You expect waves 2 in form 2. I mean in form 3. This is for form 2 right now. I will take you through the several slides I've prepared for you concerning waves 1. I always tell you that whenever you see a topic that has 1, it means the second one is still on the way. So for today, we are dealing with waves 1, waves 2 on the way. Uh, we will start by looking at the objectives. By the end of this topic, you should be able to describe the formation of pulses and waves, describe a transverse and longitudinal waves, define amplitude, wavelength, frequency, and periodic time, derive the relation V is equals to F lambda. We call it the wave equation. Solve numerical problems involving the wave equation. What we are going to see is the content is derived from the objectives, the pulses and waves, transverse and longitudinal waves, amplitude, wavelength, frequency, and all those is what we are going to check on. So now, let me just take you slow one by one. We start from this point, just a minute. Yeah, we were here. Amplitude, wavelength, frequency, periodic time, the wave equation. Then we do some few calculations on the wave equation. Yes. Now we start. So first of all, wave. Wave is a very big thing. It's a very big, topic. In terms of, it's wide. We have sound, we have light. All of them are waves. But specifically, we have just narrowed down so that we deal with the wave itself. But in your mind, know that sound is a wave, light is a wave, and many other waves. So now let's start from here. First of all, I would like you to know what's a wave. A wave is a transmission of a disturbance. When, for example, you throw a stone inside the water, or kama uko na mtoto mdogo akikusumbua, mrushe ndani ya pool, she will create some waves. So where you have thrown that stone is where will produce the disturbance, because you have disturbed the water. Then you will see that the disturbance moving up to the edge of the swimming pool. It's not the water that moves, it is the disturbance that moves. So the disturbance being propagated. So in short, wave refers to the transmission of a disturbance. It occurs when energy is transmitted from one point to another. Let's look at this. Let's classify waves. We have different forms of waves. We can classify waves in very many ways. We can classify depending on whether they require a material medium for them to be transmitted, or whether they vibrate in right angles or in a way that is parallel to the wave travel. I will explain all this in our due slides. So the first classification is what or when or if they require a material medium for transmission. That is electromagnetic waves and mechanical waves. Tuanze na electromagnetic waves or electromagnetic waves. These are waves which do not require material medium. Whenever you ask what are electromagnetic waves, they are those waves that do not require material medium for transmission. Example include radio waves. You know radio, you can hear your vernacular from where you are. Wako Nairobi lakini wewe uko Kisumu, but you can still hear them. They do not require material medium. Radiant heat. The heat that you can feel 3 meters away from the Jiko is a wave. It's called radiant heat. It doesn't require material medium. Microwaves do not require material medium. So those are the examples of electromagnetic waves. Let me say it is, They are transverse in nature, though I will still explain when I will be explaining about transverse waves. So those are the examples of electromagnetic waves. And we have said electromagnetic waves are the ones that do not require material medium. Mechanical waves, they are the waves that requires material medium for transmission. The main is sound wave, followed by water wave. For water wave to move, they require material medium, which is water itself. There will be no water wave without water. So the medium for transmission is water, and the type of the wave is water waves. Sound, yes, it requires vibration of the molecules for it to be transmitted. That's why in vacuum, sound do not move. You cannot hear any sound in a vacuum. Those are the two examples of what? Mechanical waves. Let's classify these mechanical waves. Leave alone the electromagnetic waves. Let's classify mechanical waves. Transverse and longitudinal. I will show you this one using a diagram. For example, in transverse waves, the vibration of the particles is at right angles to the direction of the wave travel. Examples of transverse wave are water waves. Waves on a rope swung up and down. Rope. Transverse waves travel as a series of crests and troughs. This is an example of a transverse wave. The vibration of the particles is up and down. When the wave is moving in this particular direction, the transverse wave, the vibration of the particles is up and down in such a way that they are at right angles to the direction. This is the kind of the one I'm talking about. If you have a slinky spring in your lap, it can be used to illustrate transverse waves. At the same time, the same slinky spring can be used to illustrate longitudinal waves. I will explain to you. Slinky spring is a very nice spring. Though fragile, it can easily be destroyed. My class destroyed it when I was explaining to them. I don't know. Okay, let me not say it. Now, longitudinal wave, because that's what I wanted to explain to you. Longitudinal waves are the waves in which the particles vibrate in such a way that it is in parallel to the direction of the wave travel, like this one. They vibrate back and forth. But remember, at the end of the day, the particles do not move. It is just vibrating within a mean position, but they do not move. Even in water waves, it is just the energy, the disturbance being transmitted. They do not move. Even in a spring, those spirals will never move to the other side. It is the energy being transmitted through the spirals. Let me put this phone to silent. Somebody is texting me. I don't know why. So that is longitudinal waves. So mechanical waves are divided into two: transverse and longitudinal waves. Yes. Formation of longitudinal waves can be illustrated by vibrating a slinky spring at one end, to and fro along its length. That is it. Now, there's another type of a wave that I'm not going to fix either as mechanical, electromagnetic, transverse, or longitudinal. It's called a progressive wave. It is a wave that moves continually away from the source. An example of a progressive wave is a water wave. Sound also qualifies to be a progressive wave because when you shout, it moves away continually from you. Another very important question: explain why the amplitude of a progressive wave decreases gradually from the source. As the wave moves away from the source, the energy is spread over an increasingly large surface area or increasingly large area. Even if I shout here, by the time somebody who is at a distance of 200 meters will not hear as somebody who is 10 meters from me. Why? Because as the sound is being transmitted, it spreads over a large area. So the energy is spread. That's why the amplitude decreases. Even water waves. When you throw a stone in water, then the waves are produced. As they move away from the source, the energy spread over a large area and the amplitude decreases. Of course, this is what we have been learning at your exercise. I will not answer it for you. Differentiate between electromagnetic and mechanical wave, giving an example in each case. State two categories of waves. State two types of mechanical waves. State the difference between them. Give two examples of mechanical waves. Hey, you just go back to the previous slides. Uone one by one mpaka ujibu hizi zote. Haita kushinda. They are very simple. A pulse. A pulse is a special type of a wave. It is just a single disturbance. When you disturb the rope once, it produces a single disturbance being transmitted. We call it a pulse. You can tie a rope on one end, then ushikilie hii side ingine, then you just disturb it once. You will see a pulse moving. So a single disturbance is a pulse. So a pulse is a single disturbance that is transmitted through a medium. It can either be transverse or longitudinal in nature. You can decide to move up and down or along the direction. Yeah, it's a rope that can be used actually to demonstrate that. Now, all the time when we are demonstrating waves, we use a sine curve like the one you are seeing right now. So a wave goes up, down, up, down. In the process, it creates a curve. So there are 6 terms that we are going to check on one by one. When they are just in this manner, the upper part here, we call it we have the crest and the trough. The crests, the troughs. So the distance between one crest to the other is called wavelength. Or the distance from one point to another similar point, to the next similar point, that's the wavelength. Or from trough to the trough. Like now, check on this diagram. From this point where my cursor is, the lighted cursor, from here up to here, wavelength. From this part up to this part, wavelength. From this part up to this part, another wavelength. I can even decide from here mpaka hapa, wavelength. Or you see here, this part up to another similar point upper, that's also a wavelength. So how do we define wavelength? Distance between two successive crests, or distance between two successive troughs. Or the general definition is this: distance between two successive points in a wave. That is a wavelength. Amplitude is the maximum displacement on either side of the mean position. The mean position is this line. The mean position is this line. The mean position is this line. Up, how high has it been displaced up? That length that I'm saying how high is amplitude. And the units for amplitude is meters, because it is distance, just like wavelength, meters. So on either side of the mean position. Now, let's check on this. Oscillation. When a pendulum is oscillating, if it moves from D to E to F and then back to D, that's one complete oscillation. It's like a complete wave. That one we will check on it as we are moving on. So oscillation, an oscillation is a complete to and fro motion. Amplitude, we have said it is the maximum displacement of a particle from mean position. SI unit is the meters. Wavelength is the distance between any two particles in a wave that are in phase. It is denoted by a Greek letter lambda. This letter is called a lambda. It's a Greek. Its SI unit is still meters. Look at this. Particles in a wave are said to be in phase if they are oscillating in the same direction and at the same level of displacement. Of course, like this one. So you can see now, this is a wave moving. So the particles are vibrating and they are in phase. But look here, particles A and D, B and E are in phase, but C and D are out of phase because their C is getting downwards, D is getting upwards. They are out of phase, 180 degrees out of phase. Anyway, look at these three graphs here. The first one, I hope you can see. The first one, the two waves have the same wavelength. Of course, the same frequency, but different amplitude. So we say different amplitude oscillations in phase. Just a different amplitude. Anything else about the wave is the same, but just a different amplitude. Look at the second one. The second one is all of them are oscillating from the same, or the wave are originating from the same point. We say 180 degrees out of phase. The last one, 90 degrees out of phase oscillations. 180, 90. The first one we say they are in phase. Let's continue. Period. It's the time taken by a particle to complete one oscillation. SI unit of a period is the seconds. Time taken to complete one oscillation. Time taken by a particle to complete one oscillation. Don't confuse this with the frequency. It is the number of complete oscillations made by a particle in 1 second. That is the frequency. F. Frequency small f. The number of complete oscillations or full wavelength made by a particle in 1 second. SI unit of the frequency is hertz. So let's look at the relationship between frequency and period. So it's very simple. F is equals to 1 over t, or t is equals to 1 over f. Frequency is simply the reciprocal of period, and period is the reciprocal of frequency. Lastly, speed of the wave. It is the distance covered by a wave in 1 second. Frequency, it's the distance covered by a wave in 1 second. Just like velocity. Now, this is the wave equation. Just check on it. We are supposed to follow one by one until we get v is equals to f lambda. The wave equation relates speed, wavelength, and frequency. So, unajuanga speed is always the distance over time. That's what you always know. Speed is the distance over time. But because we are dealing with waves, then our speed, we are going to give it v. No problem there. Distance is the wavelength. Then period, it is t. So it's like now, v is equals to lambda over t. But you know t, you know t, you can make it f. Because in our wave equation, we don't have t. So we have to convert t to f. So t is equals to 1 over f. And by the end of the day, you just realize that f is equals to 1 over t. And therefore, your equation will be v is equals to f lambda. This is the wave equation. You will use it to answer a question. Keeping the velocity constant, f and wavelength will be inversely proportional. When you increase frequency, wavelength goes down. And when you increase wavelength, frequency goes down. This is the equation, the graph of frequency versus wavelength, keeping the velocity constant. There is an example there that I want you to answer it. I want you to go through this example. We will go it together. State the amplitude. Unaangalia the maximum displacement on either side. For me, if my eyes are not corrupted, it is 3 centimeters. Periodic time. First of all, unless you know what is periodic time, you will not answer this. So what is periodic time? Time taken by a wave to make one complete oscillation. time taken by a wave to make one complete oscillation. So ndio hii. From hapa, just to look at where my cursor is, up to here, it's one complete oscillation. And it's from 1 to 9, so it is 8. 8 times 10 power 3 seconds. Frequency. Now frequency is simply 1 over t. We already have our periodic time up here, so frequency is 1 over t, what we have here. Then wavelength. Now let me tell you how you will get this wavelength. I will show you the workings in my next slide. Wavelength, from the wave equation, V is equals to lambda f. Now we are looking for the lambda, the wavelength, is V over f. V is the speed, and we have the speed here, 2500 centimeters per second. You can make it meters per second, equate 25 meters per second. Then you divide by the frequency. Our answer in C, as simple as that. That is how they are done. Just to check on it. Itakusumbua sana. Yeah. So that is over. Now allow me to give you an exercise, and the first one is whatever you are seeing over there. I'm giving you like 12 questions, and I'm just displaying so that you can just see it over there. Kazi yako ni kukopi na kufanya. You post the screen, you copy, you do it. Twende ya pili, you post the screen, you copy, you do it. Twende ya tatu, you post that screen, you copy, you do the questions. Haitakushinda, but if you feel like imekushinda, you just text me. My number is always there on the description box. My WhatsApp number. Just text me. The revision exercise in waves number 6, number 7. I did not get it. I will do it for you. Yes, number 9, 10, and 11. Those are the questions that I expect you to post the screen, to copy it. Then I know all is well. Yes, haitakushinda. Number 12 iko hapo. Just work on it. It's for you. Apply what we have been discussing there, and you will get it. Thank you. I always say, after watching my video, don't forget to subscribe. Don't forget to like. The thumbs up. Don't forget also to make a comment. Mwalimu akimaliza kufunza unamwachia ka comment hapo chini. Thank you for the lesson. Then you can share with other people. God bless you.